Hello, so this is the second part of videos on the moment of inertia of a timber I-beam formed using three timber parts. So this is the structural analysis made fun and easy channel. Please like the video and subscribe to the channel for more content like this. Just tried to smarten up the presentation a bit. So I'm still tagging this simply supported beam because if you look at part 1 and part 3, there's a little bit more about simply supported beam analysis. So basically in this question we were asked now, this is part part C, this is determine the second moment of area of the cross section about the neutral axis. So in the previous video I determined the position of the neutral axis, and as you can see just about, you should be able to see there, the position of the neutral axis is 101.67 millimeters above the bottom of the section. So just to recap, we got I-beam. It's made of three sections of timber, so three sections of rectangular timber. That's section 1, that's section 2, that's section 3, and then it's glued together here at the joints, and here where the web is just glued to the flanges. This is the top flange and the bottom flange. That's 250 wide by 20 millimeters. The overall depth of the section is 240, and the width of the top flange is 150, and the width of the bottom is 250. So the diagram, this is just the diagram of the section showing the areas and the notations of the components. So what we got to do now, I found out the neutral axis in the previous video, so now we've got to calculate the moment of inertia about the x-axis neutral axis. So basically to do this, what we have to do, we've got x-axis of the entire section. The second moment of area of the entire section is equal to the sum of the ix of each section plus the area of the section times the dx squared of each section, and then we add them all up to give us a total value. So it just means that the ix of each section is the second moment of inertia, and because they're all rectangular, that's BD cubed over 12. The dx is a distance from the centre of area of the section rectangle under consideration to the neutral axis. There's no need to use plus or minus in those calculations. And so just show an example. So for section 1, dx is equal to the distance from the neutral axis, which is 101.67 above the base of the section, to the centre of area of the first section under consideration. So that is equal to 20. That's equal to 20 plus 200 plus 20 over 2. That gets you to the centre of area of section 1, and then just minus the distance from the neutral axis. So that's 20 plus 200 plus 20 over 2 is 101.67, which is 128.333 millimeters. And so for the other sections, you just do the same thing, you just keep on doing the same thing. The dx is just the distance from the neutral axis, which is that one, to the centre of area of the section. So for example, section 1, the centre is there, which is 20 over 2. Section 2, the centre is about there, it's 200 d over 2. The same thing with this one, d over 2 is centre there. Back into the equation. So the ix of the entire section is equal to each section, the total of ixx of s plus as plus dx squared, and as is simply the area of the section under consideration. So all we have to do is work out the IXX plus ASDX squared for each section, which is IXXS plus ASDX squared. So for section 1, as above, it's IXX for a rectangle is BD cubed over 12. So we know roughly for the first section, B is going to be wide, it's 150 wide times 20. For the second one, it's 20 wide times 200 deep. And for the section 3, it's 250 wide times 20 millimeters. So section 1, dx, as I showed, is 20 plus 200 plus 10 minus 101.67, which is 128.333. AS dx squared is therefore 150, which is the wide, times 20 deep, times 128.333 squared. When you work that out with a calculator, you get 49,408,333.308 millimeters to the power of 4. And IXX for this section 1 is BD cubed over 12, which is 150 wide times 20 deep cubed divided by 12. That gives you 100,000 millimeters to the power 4. So the total IXX contribution for this section is equal to 49,408,333.303 plus AS dx squared, which is 100,000. That gives you 49,508,333. So just repeat the process for the other two sections. So you got dx equals 20 plus 200 over 2 minus 101. I'll put the text in the video, in the description of the video. And then IXX equals BD cubed over 12 for section 2, which is 20 times 200 to the power 3 divided by 12, which is 13,333.33. And AS dx squared again for section 2 is 20 times 200 times 18.33 squared. That's 1,344,443.96. When you add them together, you got 14,677,779.29 for section 2. Then finally for section 3, dx is equal to 101.67 minus the distance from the bottom to the middle of the section 3, which is 20 over 10, so it's 101.67 minus 10, so that's 91.67. That's 91.67 there. So you've got AS dx squared is 20 deep times 250 wide times 91.67 squared equals 42,016,944.5. And the IXX equals 250 wide times 20 to the power 3 divided by 12 is 166,666.666. So the total IS for section 3, the total contribution is 42 million plus AS dx, which is 166.6667 thousand, equals 42,183,611.1667. So then we just add them up to get the total IXX value. So it's section 1 we calculated was 49,508,333.30 plus 14,677,777.29 for section 2, which is that value, and then we got 42,183,611.16 for the final section. So the total of that is 106,369,721.76467 millimeters to the power of 4. So I know this is actually correct because I checked it using Procon Structural Engineering demo version. So the answer is rounded up you could either say 10.637 times 10 to the power of 7 millimeters force, or 1.0637 times 10 to the power of 8. So that's how you get the answer. It's pretty easy to calculate the second moment of area. Just basically split the section up into 3 sections, 3 rectangles, and then work out the IXX about its own axis times the area times the square of the distance between the centre of area of the section and the neutral axis, and that basically gives you the entire second moment of area. So hopefully you found this useful. Please like and subscribe, and then I can do some more videos. Thanks.